Hello everyone, welcome to Computer Aided Design course code P20DE102. I am B. RAKESH, Assistant Professor in Department of Mechanical Engineering, Kids Warangal. In this video lecture, I am going to explain one topic, that is b-spline curves. In previous video lecture, I have discussed about Bezier curves. Synthetic curves are basically classified into three types. One is hermetic cubic b-spline curve, second one is Bezier curve, third one is b-spline curve. Today's video lecture, I am going to explain what is b-spline curve and what are the properties of b-spline curve and what is the basic function of b-spline curves. This topic learning objective is parametric representation of b-spline curves. After completion of this topic, student will able to learn determine the parametric equation of b-spline curves. This is the this topic course outcome. Let us see the major difference between Bezier curves and b-spline curves. Bezier curves depends upon global control points. In b-spline curves, it depends upon local control points. Bezier curve degree of polynomial depends upon control points. Based upon control point, curve shape will be established from starting point to the end point. In b-spline curve, degree of polynomial does not depend upon control points. It depends upon the order of polynomial, that is based on number of control points. If order varies, then blending function degree will be different. In Bezier curve, if you change any point of the in the Bezier curve, if you change any point, the complete shape will be changed. In b-spline curve, if you change any one of the point, only that portion will be changed, not complete the shape. Let us see one example. Bezier curve. This is it depends upon global control points. Now I am taking point 1. This is the point P1. This is the point P2, that means control point P2. This is the control point P3. Now I am drawing the curve, that is P1 to P3. This is the resulting curve of Bezier curve. Now I am changing control point P2 to from here to here. This is the P2 star. That means this is the new control point. The resulting curve will be established like this. In the Bezier curve, if you change of any point, the complete shape will be changed. In the previous one, P1, P3, the resulting curve. After I am moving control point from this point to this point, that means P2 to P2 star. This is the resulting curve after changing the point from P2 to P2 star. So this curve totally depends upon global control points. Now I am going to explain one example for b-spline curve. Now I am taking control points. This is the P1, P2, this is the P3, P4, this is the P5, this is the P6. Based upon these control points, I am drawing the curve. P1 to P6. Uh, this is the convex hull. I am dividing curve into number of equal segments. This is the point K1. This is the another segment K2. This is the another segment K3. Here I am dividing curve into number of equal segments. These equal segments are called as knot vector or knots. K1, K2, K3. These are the knots. Wherever the control point position changing, that portion will be the portion of that curve will be changed, not complete portion. For example, I am changing point from P2 to P2 star here. In previous one, Bezier curve, the entire shape will be changed, but in the b-spline curve, only this portion, that means P1, K1 portion will be changed. This is the final resulting b-spline curve. That is the difference between Bezier curve and b-spline curves. In the Bezier curve, this is in this, when we, if you change any point of the complete shape will be changed. In the b-spline curve, only that part, that segment part curve will be changed. That is the major difference between Bezier curve and b-spline curve. Let us see the let us see the summary of b-spline curves. B-spline curves have the ability to interpolate or appropriate a set of given data points. Interpolation is useful in displaying design or engineering results such as stress or displacement distribution in a part, while approximation is good to design free-form curves. Interpolation is also useful if the designer has measured data points in hand that must lie on the resulting curve. We will discuss these 3 points in the properties of b-spline curves. Already we discussed about the major difference between Bezier curves and b-spline curve. Let us see the summary of the difference between Bezier curves and b-spline curves. In contrast to Bezier curves, the theory of b-spline curves separate the degree of the resulting curve from the number of given control points. While 4 control points can always produce a cubic Bezier curve, they can generate a linear curve, quadratic curve, or cubic b-spline curve. This flexibility in the degree of the resulting curve is achieved by choosing the basic function, that means blending function of b-spline curves, with an additional degree of freedom that does not exist in Bernstein polynomials. Let us see the basic function of b-spline curve. These basic functions are the b-splines, the name b-spline curves. Similar to Bezier curves, b-spline curve defined by n plus 1 control points. Let us see the b-spline curve. Pi is given by p of u equal to summation of I equal to 0 to n pi n I comma k of u. The ranges from u minimum to u maximum. Here u minimum is 0. 0 less than or equal to u less than or equal to u max. Here n I comma k are the b-spline functions, where k is the order of b-spline curve and n is the number of control points. Here the control points, sometimes called d-Bour points, from the vertices of the control are d-Bour polygon. Let us see the properties of b-spline curves. The sum of b-spline basic functions at any parameter u equal to 1. Already we discussed in previous slide. You can see here the first parameter properties, the sum of b-spline basis function at any parameter u equal to 1. Here the resulting curve is divided into number of equal segments. The sum of equal segment, this is the one segment, this is the second segment, this is the third segment, this is the fourth segment. The sum of these these segments equal to 1. That is the first property. That means partition of unity. P of u equal to summation I equal to 0 to n I comma k of u equal to 1. That means the sum of b-spline basis function at any parameter u equal to 1. Let us see the second property, positivity. That means n I comma k of u greater than or equal to 0. The basic function is always positive or 0. Here the basis function is summation I equal to 0 to n I comma k of u. This basic function is always positive or 0 for all parameters. That is n I comma k of u always greater than or equal to 0 except for k equal to 1. Each basic function has one maximum value. Let us see the third property. The support of each basic function, that means n I comma k of u is compact and contained in the interval, that means ui comma u I plus k plus 1. The next property is continuity. Here the basic function is k minus 2 times continuously differentiable. Let us see the next property. The maximum order of the curve is equal to number of vertices of defining polygon. Next property, the degree of b-spline polynomial is independent on number of vertices of defining polygon. B-spline allow the control. B-spline allow the local control over the curve surface. Already explained in the first slide. If you change any point in the control point, only that portion will be changed, not complete shape. So that's why b-spline curve having local control points. B-spline allow the local control over the curve surface. Here the curve lies within the convex hull of its defining polygon. Already I said you can take Bezier's curves or b-spline curve or a Hermite cubic spline. You can take Bezier curve or b-spline curve. The curve must and should in between within the convex hull. For example, this is the P1 point, this is the P2 point, P3, P4, P5, P6. This is the convex hull. This is the resulting curve. The curve lies within the convex hull of its defining polygon. You can change the point. You can change the any one of the control point from its original position to new position. Only that shape will be changed. This is the P2 star. The next point is the curve generally follow the shape of defining polygon. These are the few important properties of b-spline curves. The b-spline function also has the property of recursion, which is defined as n I comma k of u equal to u minus xi into n I comma k minus 1 of u by xi plus k minus 1 minus xi plus xi plus k minus u into n suffix I plus 1 comma k minus 1 of u by xi plus k minus xi plus 1, where here I am taking k equal to 1, n I comma k equal to 1. This condition is applicable for the u limits are xi, the u lies in between xi plus 1, n I comma 1 equal to 1. The condition is xi less than or equal to u less than or equal to xi plus 1. When I equal n I comma 1 equal to 0, for all other conditions, that means xi less than or equal to u less than or equal to xi plus 1, other than this condition, the basic function n I comma 1 equal to 0. Let us see, n I comma 1 equal to 1 when where the u lies in between xi less than or equal to u less than or equal to xi plus 1. Other than this condition, the basic function n I comma 1 equal to 0. Here xi are called parametric knots or knot values. This is the very important term. Here xi are called parametric knots or knot values. These values form a sequence of non-decreasing integers called the knot vector. When we designing the b-spline curve, we have to evaluate knot vector based on number of control points and order of curve. In the starting slide, we discussed about the difference between Bezier curve and b-spline curve. B-spline curve does not depend upon control point. It depends upon both control points and order of curve. Here, knot vector can be evaluated by three parameters. First one is uniform, non-uniform. Third one is open uniform. Let us see the formula for open uniform knot vector. Xi equal to 0. The condition is I less than k. Xi equal to 0 when I value is less than k value. When xi equal to I minus k plus 1, when I lies in between k and n, that means k less than or equal to I less than or equal to n. Xi equal to n minus k plus 2, where I value is greater than n value. Here n means number of control points. I hope this is very clear to everyone. Okay, after completion of this b-spline parametric representation of b-spline curve, the student will able to determine the parametric equation of b-spline curve. In next video lecture, we will discuss few numerical problems on b-spline curve. Thank you for watching. Please do like and subscribe my channel for more videos.